Hello, let's talk about mean and standard deviation of a probability distribution. Now, real quick reminder from Unit 1, way back at the beginning of the year, we talked about how the shape of the distribution can give you information about mean and median, those other measures of center. And so when distributions are skewed, the extreme values tend to pull the tail in that direction. So we say the mean follows the skew. So when we have a distribution like here on the left, this is skewed to the left. I can see that the tail is trickling out to that left side. The mean is going to be left of the median. And the mean is going to be the lesser value. The mean follows the skew. In an approximately symmetric distribution, the mean and median are usually about the same. And then in a distribution that is skewed to the right, the mean follows the skew. The mean tends to be pulled by those extreme values and is greater. It's on the right side of the median. All right, so with that being said, a probability distribution from yesterday. Remember, this is a random variable, is a numerical variable whose result is the outcome of chance, of some sort of chance experiment. And since this value is numerical, we can actually describe the distribution using these ideas of shape and center and spread. Okay, so if we're talking about, for example, over many months, a nurse keeps track of the number of patients who call during the first 30 minutes that the doctor's office is open each day. Assuming the following histograms represent the probability distribution of the random variable x, where x is the number of patients calls on a given day during the first 30 minutes. And so I have these three different distributions. You can see that on the x-axis, we have the number of patients who call during those first 30 minutes. Okay, those are discrete values, 0, 1, 2, 3. They're numerical results of counts. In the vertical axis, we have probability. So in that case, we're talking about probability as a long-term relative frequency. So in this middle graph right here, it looks like 0 people called about 2% of the time. So that means over a very large number of calls, about 2% of them said 0. Okay, so we're going to read these as probability distributions. And since they are numerical, we can say things like, it looks like the center is approximately here. It looks like the shape is approximately this. Okay, so we can talk about it using those socks. All right, so on this first one, okay, so if I was to look at this and we were to first talk about this shape, okay, it's definitely going to be skewed to the right. Looks like it's unimodal. It's got a peak at about one patient. It's trickling off to the right side. It has more brows on the right of the peak. And we would expect then that our mean would be larger than our median because the mean is going to follow the skew and be a bigger number. We know the median's at the 50th percentile, so if I wanted to estimate that from the picture, I'd start looking at the probabilities. It looks like 0 here has a probability of about 28%. So I'm looking at 50% at or below, so that's not quite it. If I go to 1, between x equals 0 and x equals 1, x equals 1 looks like about 32%. That cumulative probability is going to be 60% at that point. That means that 60% of the values are at or below the number 1. So if 28% are in the 0 and 32% are in the 1, then that 50th percentile is going to hit in the middle of that 1 too. All right, so that means my median is 1. And then because this is skewed to the right, we would expect the mean to follow the skew. So we would expect that mean to be a larger than 1 value. All right, now this guy, we look at this. This looks approximately symmetric to me. It looks like my little face is in the wrong place. So approximately symmetric. It's rough. It's not perfect, but peaks in the middle, sort of drifting off on both sides. Since it is approximately symmetric, we would expect the mean and median to be about the same. So if I'm looking for that 50th percentile, and since this is approximately symmetric, we're going to say it's probably 3 because that's the peak and it's symmetric. But if we were going to count just to be sure, x equals 0 looks like about 2%. X equals 1 gives me about 11. Put those together, the cumulative probability is about 13%. Still not at that 50th percentile yet. We could tack in that bar for 2. That one looks like about 23%. Put those all together. We're still only at 36%. Haven't hit that 50th percentile yet. So I'm going to go to the bar for 28, and that gets me to 64%. So the 50th percentile has got to be in this bar for the 3. Okay, so that means my median is 3, and I would expect my mean to be approximately 3 as well. All right, now this one right here looks like it is skewed to the left. We have a peak at about 5, tailing off on that left side. All right, so if it's skewed to the left, we would expect the mean to be less than the median. In other words, we'd expect the mean to be pulled in the direction of that tail. It's going to be a smaller value affected by those low values there. Again, median's at the 50th percentile, but I'm guessing that it's probably over here on the right side. So remember, 50th percent at or below also means 50% above. And it looks like I might get a better chance of counting in that direction. So I start off with x equals 6. That's about 9%. That would give me 91% at or below 5. Okay, if I put in the 5, that's 30% here and another 9%. Those two bars together just make me 39%. That's going to be 61% at or below. And here we have another 25%. So that puts 64% above and including 4. So we would know that the median is going to have to be in that spot because there's 50% above at that point as well as 50% below. And if you wanted to add up all these little ventures in there, well, we think the median is about 4, and we would expect that mean to be less than the median. All right, so one of the things that you need to be able to do is actually compute this when you don't have a graph, when you just have data. So the mean and standard deviation are going to describe center and spread for a probability distribution. So this is on your formula sheet. This is a snip from your formula sheet. It says for a discrete random variable x. So we're talking about a counting variable. It's a result of a count, 1, 2, 3, 4, 5, 6. It's a random variable, means it's a result of chance, and it's a numerical outcome, which is why we can find the mean, because the mean is the average. Okay, so, and notice we have this symbolism here, mu sub x, and then it says equals e of x equals the sum of x, and you can't see this very well because of my snip, sorry, of an I times p of x I. And then standard deviation has this crazy square root thing going on here. All right, so a couple of things. Since this is a probability distribution, we're thinking the sum of all the outcomes has to add up to 100%. That's one of the characteristics of a probability distribution. So if it's adding up to 100%, we consider this thing to be a population, and we use population notation. So those Greek letters of mu and sigma for our mean and standard deviation. So for mean, we're using this mu of x. Okay, and if the x is not there, that's fine, but this allows us to talk about different variables, like maybe we have mu sub x and mu sub y, or maybe we have mu sub female and mu sub male, and we can keep track of different means and different variables at the same time. Now, to find the mean of x, okay, the mean of a probability distribution, this variable x, what we're going to do, this says take the sum of every x times its probability. Okay, so keep this, all this is saying, take every x value times the probability of getting that x value. Okay, there's this e of x here, which means expected value of x. What would we expect to get if we did this random experiment? As far as standard deviation goes, that's the other one on your formula sheet. That one is sigma sub x, so that Greek sigma instead of that lowercase s for sample. Okay, and to find this, it's every x value minus the mean squared, because that makes it positive, times its probability. Okay, so this is very similar to the way that we found standard deviation before. How far away from the mean is it? Squared, so we're talking about positive distance, and then that square root helps take care of that. And again, and then we've got this probability in there because of the weighted differences. To find the variance, you square standard deviation. So sometimes you might see that as literally the standard deviation squared, or sometimes you'll see it as sigma squared of x. That's variance. And just a little note there that e of x means expected value. All right, so these are on your formula sheets. On your formula sheet, this is not something you have to have memorized, but it is something you need to know how to use. All right, so a couple other things really quick. A numerical value measuring a characteristic of the population or the distribution of a random variable, that's known as a parameter. Again, so because we're talking about a population of this distribution of this random variable, we're going to use mu and we're going to use sigma. Parameters for discrete random variables should be interpreted using appropriate units and in context. Okay, so for example, we talked about the mean before. We would say this is a typical value of the variable. This is the expected value of the variable, but it needs to be in context. What's the unit? In what are we talking about? Puppies and kittens? You know, got to make sure we refer to that. Standard deviation is the typical amount that your observation differs from the mean. Okay, so it's like on average how far away from the average it is, but it's a typical amount that our object deviates from the mean. All right, so I have this insurance payouts, okay, and it says find the mean and standard deviation of the probability distribution and interpret in context. Okay, so I've got this policyholder outcome, the payout, and the probability of getting that outcome. Okay, so what this is, a long-term probability, a long-run probability. This insurance company pays out $10,000 when someone dies, $5,000 if the person is injured and cannot go back to work, and if neither thing happens, there's no payout. So people buy insurance hoping that one of these things does not happen, but in the case that it does, it pays out. Otherwise, you've just paid in and paid in and paid in and never got that payout. But that's actually kind of what you're hoping happens in this case. Now, the probability of this happening, we have 1 over 1,000, 2 out of 1,000, and 997 out of 1,000. Notice those add up to 1,000 out of 1,000 or 100%. And the idea here is this is a long-term probability. The insurance company have noticed that they have to pay out once for every 1,000 customers, basically. Problem says here, find the mean and standard deviation and interpret in context. So I'm going to start off with this formula. The mean of x is E of x, the expected value is each x value times the probability of getting that x value. So I'm going to start with that first. All right, so my first x value is 10,000 times its probability 1 over 10,000. Sum plus 5,000 times 2 out of 1,000 plus 0 times 997 out of 1,000. Okay, so it's literally each x value times its probability added together. Okay. If I do this in my calculator, I end up with 20, but I need to interpret it in context. 20 what? This is an insurance payout, so I'm going to say $20 is the typical value of an insurance payout for this policy. Okay. For the standard deviation, notice it says take every x minus the mean and square it. So I'm going to take 10,000 minus 20 and 5,000 minus 20 and 0 minus 20. So in order to find the standard deviation, I have to have the mean first. I'm going to square that and multiply each times its probability. And that square root is going to help take care of that as well. So the square root of, okay, the first one is 10,000 minus the mean, 20, squared, times that probability. I'm going to go ahead and express that as a decimal. Instead of 1 out of 1,000, I went ahead and wrote it as 0.001. Plus 5,000 minus the mean, 20, we're going to square it, times that probability, 0.002, plus 0 minus the mean, 20, squared, times 0.997. So each x value minus the mean of all the x's, quantity squared, times each individual probability that goes with those x values. You add each of those outcomes together, and then we're going to square that, and then take the square root. All right, so the square, the sum underneath there in my calculator, this gave me about 149,000. And when we take the square root, we get 386. All right, so remember, this is not in context. What is this? This is a standard deviation, and it's an insurance payout, so it's money. So $386.78 is the typical amount that an insurance payout deviates from the mean of $20. This is a typical amount that something we see happens deviates from the average thing, what we expected to happen. And the reason why that standard deviation is so large is because there's a lot of variation between 10,000 and 0, where most of the data is. All right, here's another one. This goes with our Lucky Lovers discount problem for the other day. Remember, if the person gets the ace of hearts, they win $20 off. If the person gets an ace of diamonds and then gets the ace of hearts, they get $10 off. And if they get the black ace, they get $0 off either of those extra times. All right, so this was 25% and about 8% and about 67% there, but those are expressed as decimals. So again, if I wanted to find the typical amount there, I'm going to take each x value, 20 times its probability, 1/4, plus 10 times 1/12, plus 0 times 2/3. Okay, each x value times its probability. That gives me 5.83. Now remember, what is this? This is a typical amount of the discount. So $5.83 is a typical amount of the discount. Another way to say this is an expected value. We expect someone to, on average, to win about $5.83 off their bill. Okay, here's my standard deviation. Again, I'm going to take every x, so 20 and 10 and 0. I'm going to subtract the mean and square it, and then multiply by the probability. So 20x minus 5.83, the mean, squared, times 1/4, that probability. And then 10 minus the mean, 10 minus 5.83, squared, times that probability, 1/12, plus 0 minus the mean, 5.83 squared, times that probability. I pop that in my calculator, I get about 52 under the radical. Okay, and I take the square root, I get 7.27. So remember, $7.27 is the typical amount that a discount, a value of my variable that I see happen, deviates from that mean of 5.83. Okay, now when you are doing these problems, sometimes it is very useful. Oh, I got my answer here. Oops. PowerPoint problem. It's very useful to be able to do this in your TI-Nspire as well. So spell checking checks the, I'll put my picture down here. Spell checking checks the non-word errors, which result in a string of letters that's not a word, as when the is typed te. You can see that when I typed this in Word, it actually did give me the little red squigglies underneath. When undergraduates were asked to write a 250-word essay without spell checking, the number X of non-word errors had the following distribution. All right, so basically they wrote a 250-word essay. They were not allowed to use spell check, and we wanted to see how many words that they typed that were like the correct word, but they mixed the letters up, so it's spelled incorrectly, non-word errors. And you can see that about 10% had 0 errors, about 20% had 1, 30% 2, 30% 3, and about 40% 1. So it looks like most people had about 2 to 3 non-word errors there. So find the mean and standard deviation of the probability distribution using your calculator. So here's what we're going to do. Okay, in your TI-Nspire, and I would suggest you pause the video here in a second and actually do this. Okay, you're going to create a new document with a list and a spreadsheet. And you're going to create the X with the column in a spreadsheet with 0, 1, 2, 3, 4. And you're also going to enter the probability, and you're going to type it in as P. You can't type it in as P of X because your calculator doesn't like that notation. But P of X, you're just going to type into P and put 0.1, 0.2, 0.3, 0.3, and 0.1 next to those values. After that, you're going to run the one variable statistics, just like we did back in chapter 1. But the difference is when you go to do statistics, stat calculations, one variable statistics, when it gets to number of lists, you still have one list of data, okay? The X1 list is going to be X, but you are going to fill in this frequency list option that we normally skip over with P. The frequency list tells us how often we get each of the X values. So in this case, we're going to use the probability as that frequency. Now I'm going to pause my video and bring up my calculator. All right, so here is my calculator. So I'm going to go New Document. I do not want to save my old document. I'm going to go List and Spreadsheet. And I'm going to put in my X value here, and that was 0, 1, 2, 3, and 4. I'm going to go P for probability. Remember, you have to label these so you can grab them later. 0.1, 0.2, 0.3, 0.3, and 0.1. Okay, so I've got my values here. I like to arrow over, so I'm not in one of those values. So I'm going to press Menu and Statistics and stat calculations and one variable statistics. I'm going to go back and do that one more time. Okay, Menu, Statistics, stat calculations, one variable statistics. It's going to ask me how many lists I have. Again, always just select one for this. My X1 list, what's your X variable? That's X. And then again, here's the big difference from chapter 1. The frequency list, I'm going to put P in there, probability. Click OK. And here we go. I've got X bar is 2.1. Sum of the X's, 2.1. Sum of X squared. Notice S, standard deviation, says undefined. Okay, and that's because this adds up to 100%. So we're dealing with a population, so there is no sample standard deviation here. All right, and since sigma X is 1.135. Or 136. Now also notice that our calculator gives us that X bar, but that's because the calculator, there's no computational difference between X bar and mu, and so they just give us the 1, but we know, because we know better, that this is a mu. All right, so again, sigma is our standard deviation. All right, here we go. Move my face again. All right, so in my calculator then, I get this X bar is 2.1. I get 1.136. So I can say that 2.1 errors is a typical number of non-word errors. There's my mean. And 1.136 errors is a typical amount that a number of errors deviates from that mean number of errors of 2.1. Okay, so using your calculator, very useful. So if I go back to this whole calculator thing, all right, back at the beginning, we looked at this one that was skewed to the right. And when it's skewed to the right, we expected the mean to be greater than the median. Here are those actual X and P of X values that you could either estimate off of your graph, okay, or I typed them in to make the graph so I knew what they were. All right, so here are those values. I expected the median to be 1. We expect the mean to be bigger than that. I popped these in my calculator, and I got that X bar was 1.44, and that sigma was 1.3. 0.337, etc. Okay, so in other words, this is the mean, and this is a mu, right? Because even though it says X bar, we know we're talking about a probability distribution. The mean is 1.44, and the standard deviation is 1.34 patients. You can also see the median over here. Here's the median is 1. You could compute the interquartile range. Q3, 2, minus Q1, 0, gives me an interquartile range of 2 patients. Remember that mean and median are both measures of center, and standard deviation and interquartile range are both measures of spread. Okay, so in this case, when I'm looking at this, what I thought was true from the picture is actually true. The median was 1, and the mean is larger than that, 1.44. You can tell it's being pulled in the direction of the tail. Okay, here is the other one, the one that we said was approximately symmetric. Okay, here's our approximately symmetric distribution. We said that the median we thought was going to be 3, and we would expect the mean to be close to 3 as well. Okay, so I did this in the calculator using the one variable statistics. I got that the mean was 3.03, and the standard deviation was about 1.35 patients. Okay, also you can see that the median was 3 and can compute the interquartile range for -2. Oops, 4 minus 2, and they get the same. So again, the median was 3, and the mean is really close to that. Okay, it's not perfect because this isn't perfectly symmetrical, but it is very close. Okay, all right, and then we had our one that was skewed to the left, and we expected that if it was skewed to the left, the mean was going to be 4, and we would expect the mean to be less than that. Okay, the median, so I get a mean in my calculator of 3.81 and a standard deviation of 1.46. 1.47 there. The median was 4, and my interquartile range, 5 minus 3, gives me 2. Remember, mean and median, both measures of center, standard deviation, interquartile range, both measures of spread for our socks that we need later. Okay, so the mean is, in fact, a little less. You can see it's been pulled by that tail. All right, so what do you need to know? Okay, so first off, and I got a couple things happening here, you need to use the graph of a probability distribution to estimate the center using median and mean. So just like we did before, I want you to be able to look at a graph and tell approximately where the mean and median are. You should be able to estimate where the median is using that idea of 50th percentile, because probability distributions show you the percent. And by computing that cumulative percentage in your head or by writing it out or whatever, you should be able to find that median. And then you should be able to estimate whether or not the mean or the median, whether or not the mean is bigger or smaller than the median based on the shape of the graph. All right, you need to be able to use the formula for mean and standard deviation and be able to plug in those values and evaluate correctly. Okay, got to be able to use that formula. So, for example, you need to be able to show your work on this. Like, if this is a free response question, you are expected to show these numbers plugged in. So when we calculated the mean, I would expect handwriting that looked like 10,000 times the probability plus 5,000 times the probability plus 0 times the probability. Do all that string in your calculator, but you need to show plugging into that formula that you know how to calculate that. Okay. You also need to be able to show that work on standard deviation. If you're looking at a multiple choice question, it'll say which of the following shows how to correctly find the standard deviation. So even if it's not a free response, you need to know how that formula works so that you can pick out the right answer here. Okay. Now, you also need to know how to use your TI-Nspire. So if you have a problem that says the U.S. Postal Service recently released data on the number of days it takes for a first-class letter to reach its destination, you have a probability distribution, and it says what's the mean and standard deviation. You can calculate this by hand. There's no reason why you can't. But for most of you, it's going to be faster, even in terms of a multiple choice question, to set this up in a document really quickly in your TI-Nspire and compute the mean and standard deviation and just pick the correct answer. Okay. That being said, if this same question could be multiple choice and you might have to pick out the correct way to compute it without your calculator at all. All right, so you need to be prepared for that. All right, you need to be able to interpret the mean and standard deviation in context. That means you need to be able to write that sentence. The mean is the typical value of the variable with units. And what is that variable? You need to talk about your standard deviation. The standard deviation is the typical amount that an observed value is going to differ from our mean value. Another thing you need to be on the lookout for probability distributions is the word expected value. Expected value. If they say, what's the expected value of the variable? Your brain needs to go, whoo, that's the mean. Okay, so expected value. And then finally, you need to make sure you're always using correct notation for mean and for standard deviation. So in a probability distribution, you need to know that we're talking about a mu and a sigma because it adds up to 100%. So we're going to consider a probability distribution to be basically our population. So we're talking about parameters. Don't get confused because in your calculator, it's always going to feed back X bar, but you need to know this is a mu. So when you write down that terminology, you can do that. Now, if you're not sure which one to use, you'd be better off just to use the word mean or standard deviation in words than to use the wrong symbol or notation. All right, so you can do this. Have a great day and good luck with probability distribution, means, and standard deviations.